We're going to continue our exploration of arithmetic sequences, but specifically how you write the rule or find the rule for the nth term of an arithmetic sequence. So we say the recursion form for the nth term of arithmetic sequence is given by this formula right here. So basically, I want to pick this apart. If we were talking about, say, a function like y and x instead of a sequence, this would say something like y equals, like b plus m. Let me rewrite that in here. M times x minus 1, which is an interesting story. This would give us the equation of a line. So what we're kind of doing here is the same type of thing, but this, interestingly enough, says if you want the nth term, so this is the rule for the nth term. What I'm here to tell you is you would need two bits of information here, and the first one's going to be this. You're going to need to know A1, and this is the first term. This is very true anytime you want to write the rule for a sequence. And then you need to know D, which of course we are calling the common difference, or the distance between numbers in at least an addition or subtraction sense, okay? So you're going to need to know A1 and D. So we need, if I'm making a list here, A1 and D. And I want you to consider this. If I gave you a sequence here and I said, A1 is 4, as a matter of fact, and I said D is -2, we say go write the rest of the sequence. You could see how this would be, totally sufficient to say, well, then I would know that my first term here was 4, and what's happening every time is it's going down by 2. So we would say that my A2 would be like 2, and my A3 would be like 0. And so the idea here is this. If I had an entire list of numbers, why wouldn't it be just as easy to go look at this list of numbers and say, look, I know the first term, and I know what it's changing by every time. Could we work backwards to figure out what the rule would have to be for this? So now certainly I can tell you this. We are perfectly capable of doing this and making a table of values and saying our first, second, third, and fourth terms by observation were 4, 2, 0, and -2, and like guessing the rule. We say, what am I doing to my n values to get my, my an values here? And we'd say like, an, what I notice is, I'm doubling, I guess you could say I'm going down by 2 every time. And, we'd say, what would this be, +6, something like that? 1, yep. And so like I'm negative doubling these things, but I'm adding on 6 every time, which can be hard to kind of infer by looking at this rule. So what we're going to do is we're actually going to write some rules over here showing how we could work backwards just using this formula right here and instead come up with a rule fairly easily, okay? So we say the write the rule for the nth term of the following sequences of numbers. And I've given various information here, but we know this. According to me at least, you need to only know two things to write this rule. We need to know the first term and the common difference if at all possible. So we're going to look at this one. We say the common difference is 3. Let's go ahead and write this down. We say D is 3 and the first term is 2. So this is like a meatball here. I'm throwing a softball pitch up to you. But we're saying what would the rule be? Well, according to my formula over there, we say it is always the first term. So it's going to be my A1 plus the common difference is B, common difference, and we're going to say times n minus 1, always n minus 1. And all we have to do is directly substitute in these values, okay? And so what I could tell you right here is, right there, you get some credit in my class at least for just writing that because you're saying, yeah, this is the rule for the equation. As a matter of fact, in calculus, it's very beneficial to leave things in this form a lot of the time because we're really just looking at slopes. But anyways, we say this right here should and could be simplified in most senses. So what we say, an is actually equal to 2 plus, and we're going to distribute the 3 here. We get 3n minus 3. And when we combine out the constants here, we say an equals 3n, and that'd be a minus 1. Okay, or -1 plus 3n. You could look at it that way. I get some people that write it this way. It says it starts at -1, and it goes up by 3 every time. The way you want to look at this is up to you. We say that's how you write the rule right there. So when you're given the sequence, again, don't be deterred by this. We already observed that this is an arithmetic sequence. We can see that the common difference is 3 because it's adding 3 on every time. Or we could say, 14 minus 11 is 3. And our A1, well, we got to go look at the list of numbers here, but it's 5. So again, I'll change colors here, but we say our first term is 5, a little bit quicker this time, and our common difference is 3, and we'll just take that times n minus 1. So again, here's your rule. I mean, this rule, if you want to go use this rule, it works right now. If you wanted to go say, what is A7? We could go say it's 5 plus 3 times 7 minus 1. And what we could say is, well, then the seventh term would have to be 5 plus, 3 times 6. And so it'd be 5 plus 18. So A7, nice having this rule, isn't it? We say is 5 plus 18, which is 23. And we could see that if we were to continue our list here, this is A5. If we were to go up by another 3, it would be 20, and go up by another 3. Our sixth term would be 23. So again, writing the rule, we say A1, this term or this sequence here, the only thing here is it's going down by 4. I wanted to look at one that had a common difference that is negative. And we say our first term by observation is just 9. So our rule is going to be this. We say AN is just our first term. We're starting at 9, and then what we're doing is we're changing by 4 every time. So just want to be careful here. When you distribute this negative through, you actually get 9, and it would be minus 4n plus 4. And when you combine your 9 and your 4 here, we're saying we're starting at 13 and we're going down by 4 every time. But this is the rule to find the nth term in our sequence. Now, what gets a little bit trickier is when you don't have the list of numbers and you got to write it out. And it says something like this. The first term is 5. And I'm going to write this down. We say first term is 5. What's our common difference? It says the fourth term is 21. Okay, so that's interesting. I'm going to write this down also. We say the fourth term is 21. Now, we are perfectly capable of saying, well, these are like, what, 4 apart from one another? And the distance from 5 to 21 is 16, and 16 divided by 4 is, I'm just going to fill this in. I really am. I'm going to fill this in. It's 4. We're going to get 4. But the thing here is this. When you do not have the common difference between these things, what we're going to do is we're going to plug in bits of information into this rule. So this is very important. We have this rule, and what we also know here is this. We said when A1, when we have an n value of 1, that is, we get an an value of 5. So the interesting thing here is this. This is our an value. We are going to plug this into this rule right here. We say a1, which is our an, is 5. But this was true, okay, when n was equal to 1. So we could see that we get a1 here, a1, which is 5, plus d, okay, times n minus 1. Now keep in mind, n in this case is 1. This is our first term, so our n is 1. So we say it's 1 minus 1 when we plug this in over here. I know it's a lot of substituting in, but what we end up with here is this. We get 5 equals 5 plus d times 0, but 5 equals 5. Okay. So all this kind of goes to show is this. Well, we already know the first term, you guys. If we want to find the common difference, how could we use now this next bit of information to help us? So I'm going to have to write off on the side here. But essentially we could say, all right, well, let's plug in this next bit of information. I kind of wanted to see how this works. So I said our an this time is 21. That is a4, that's what this is our an, and that's equal to 21. We say our first term, which we know is 5. We could say plus d, which we don't know, times n minus 1. In this case, we have an n value of 4. So we say 4 minus 1. So we're going to simplify this up a bit. We say 21 equals 5 plus, now d times 4 minus 1 is 3 times d. And so now we could solve for d just by, isolating the d. And we say 16 is equal to 3d. Okay. Actually, yeah, 16. And we got a 3d here, huh? Okay, well that's not a huge issue for me, I suppose, if I've not missed any of my arithmetic here. No pun intended. Then our d value is negative 16 thirds. So I suppose our rule here would be this. We would say an is equal to our first term, which our first term was 5. And we say this would be plus 16 thirds, which is our d, times n minus 1. And sorry to write over the top of all my writing there, but that would be our rule. And we could, of course, simplify it, but we could also leave it. This is our rule for the nth term. So this last one here, this is interesting. It said the fourth term is 20. We're going to write this down. So the fourth term is equal to 20, and our 13th term is 65. So we say 13th term, 65. Again, we could say 1, 2, 3, fourth term. Hey, we know the fourth term is 20. And then we say, go out, like to the 13th term here, we say A13. We know this is 65, and we know this is our fourth term in the sequence. It's not very helpful when you don't have consecutive terms. So again, what we're going to do is we're going to plug these information bits in, and we are going to solve for an unknown using a system. So here's what you're going to see me do. I'm going to grab this space of real estate over here. We're going to say A4 is equal to 20. So we're going to just plug this into our rule up here. We say if A4 is equal to 20, then our AN is 20 when n is equal to 4, when AN was 4. Okay, so we say this is our first term, which we don't know, plus d, which we don't know, times n minus 1. In this case, we have an n value of 1. So you can see here, this is my n, and this is my an. I'm just plugging these in when a was 4. So now we could simplify this, I suppose. We could say we get 20 is equal to a1 plus 3d. Now we're going to put a box around this because we need this equation. This is equation 1. We have to go grab a second equation by plugging in the other bit of information, which would have said 65 then is our a1 plus d times n minus 1, where our n in this case, this is a13, so we say n is 13 here. So simplifying this, we get 65 is equal to a1 plus 12d. So what we're going to do now is we are going to solve a system with these two equations here. And I think that I guess the most beneficial way to do it would be by, I don't know, elimination would work fairly well here. So if we were to say, let's take this whole equation here, let's take it all times a -1. And what that'll do is it'll make our A1 negative, and when we add these together, they'll cancel out. So we would get this. We get a system where 65 is equal to A1 plus 12D, which we didn't change that equation, but we multiplied this other equation by a negative. So we get negative A1 is be minus 3D. And when we add these up, you can see that we're using the elimination method here. So we get 45 is equal to 9D. And when you solve this, the nice thing here is we get a D, oh, not divide by D, divide by 9. We say, then it follows that D equals 5. So now that we know the common differences, this is the fun thing about it, we can plug this back into one of the original equations, okay, and solve for A1. So we had this equation, 20 equals A1 plus D, which is now 5 times, and in this case, I suppose, we had 3D, didn't we? We had 3D. So let me borrow this rule here. We say plus 3 times D, which is 5. That's better, we say. So 20 equals A1 plus 15. And so what this means is our A1 actually has to equal 20 minus 15, which is 5. So now we have these two bits of information. We say then the rule. Sorry to chase it all the way back down here. We say AN is our first term, which was 5, plus our common difference, which we found to be 5, times n minus 1. And for now, we can just leave it like this. So that's how you write the rule of an arithmetic sequence.